All right, this video is the 2024 FRQs for AB. Calc, we're going to start with number 4 and move through number 6 on these. None of these are calculator active, so and that's always true. Questions 1 and 2 are calculator active, and the rest are not. Okay, so we're given the graph of F, and this is shown up here. So just please notice this is F that you're looking at. We're looking at the closed interval from -6 to 7. We have a horizontal tangent line at x is equal to -2, so right in here. All right, so we have a derivative that's 0, in other words. And then F is linear from the interval from 0 to 7. So we're curving prior, but at that instant of 0 down to when x is 7, actually, we are on a straight line. R is the region in the second quadrant bounded by the graph of F, the vertical line x equals -6, and the x and y axes, and it's labeled on here. This is easy to miss. Region R has an area of 12. Now that's a positive 12. The reason I know it's positive is because the area that is bound is trapped above the x-axis. All right, for part A, the function g is defined as g is the definite integral from 0 to x of f of t dt. We want to find the values of g of -6, g of 4, and g of +6. All right, so starting off on this one, if I want to find g of -6, I've replaced x with -6. So this is the definite integral from 0 to -6. I've replaced x of f of t dt. Because that is upside down and we have the lower limit on the bottom, I'm going to go ahead and make this a negative integral from -6 to 0 of f of t dt. This is an area model, so it makes more sense to go from left to right. But I am going to have to change the sign of this. All right, so from -6 to 0, we actually were told that area already is +12. However, I have a negative in front of the integral, so this would be -12. There is no real work here outside of setting up my integral, and so my answer is -12. Part B, I want to find g of 4. So g of 4 would be the definite integral from 0 up to x, which I'm now using 4, of f of t dt. So again, I'm using an area model. So that's the area of this triangle. We were told that this is a straight edge right here. So that would be 1/2 of base times height. Make sure you show your calculations here. They want to see the 1/2 base times height format and what you're writing out, and then that answer is 4. By the way, you actually don't have to simplify that. You could just leave it 1/2 of 4 by 2, and you would get full points for that problem. Part C, we're going to do g of 6. So g of 6 would be the definite integral from 0 to 6 of f of t dt. Again, using the area model, I have 1/2 of 4 by 2, which I just calculated as 4, and that was a positive area because I'm above the x-axis. And then I have another triangle that is going to end at the 6. Right in here, this triangle is below the x-axis, so I'm going to use a negative area. So minus 1/2 of the base is 2 and the height is 1. So I end up with 4 minus 1, which is 3. Now, you can compute that, or you could leave it in the non-simplified form. As long as everything's all numerical, you are allowed to leave fully numerical answers unsimplified. All right, part B. For the function g that was defined in part A, find all values of x in the closed interval from 0 to 6 where the graph of g has a critical point. Well, g is going to have a critical point where it has a derivative that's equal to 0. So I usually do a little bit of side work. This is actually very common for me to do whenever I have two different functions that are described in terms of each other, and one of them is an integral. I very commonly anticipate that they're going to need some derivatives. So I usually use my first rule of algebra and take the derivative of both sides. The derivative of a definite integral by the second fundamental theorem of calculus would become just f of t. G double prime then would equal f prime. Usually we don't need to go past the second derivative to g, so that's a good place to stop. But this is a nice little reference sheet. It also kind of secures some points on the AP exam. Quite commonly you need to state these things, these relationships, but it also will help me for trying to do a problem like B. So for B, what I'm trying to say is that to find a critical value, I want the derivative, which I just said, of g, which I just said is f, and I need to set that equal to 0 and solve. So if I look at my graph here of f, I'm trying to see where does this equal 0? Well, that means where does it have a height of 0? Well, that's at 4. So I have a critical value here at the instance when x is equal to 4. That's the only work that I need to do on this problem, is just saying that I'm looking where g prime, which is the same as f, is equal to 0. Part C. Now we have a new function h. H is described as the definite integral from -6 to x of f prime. We want to find h of 6, h prime of 6, h double prime of 6, and again we want to show the work that leads to the answers here. Okay, so if I want to find h of 6, I'm going to replace x with 6, so this would be from -6 to 6 of f prime of t dt. Now notice we have an integral and a derivative. Those undo each other. We don't have any variables for my limits, so the way they undo each other is they just go back to f, and then this needs to be evaluated both at 6 and -6. So in other words, this is f of 6 minus f of -6. And I can look at my graph for these values. F of 6, they told me 6, -1 is a point on f, so that would be -1. And then minus f of -6, they gave me that as 0.5. I could leave this just like that if I wanted to, or if I wanted, I could choose to simplify that to -1.5. The next part of C is I need to find h prime of 6. So h prime of 6. Well, let's think about this really quickly. Maybe let's do a quick little side work. If h of x turned out to equal the integral here from -6 to x of f prime, then h prime of x, we would now undo this integral. This would equal f prime of x, but we also have this lower limit here. Don't forget that. That's also f prime of -6. That does not just go away here. That is still part of the problem. So I'm still evaluating these at two different things here. So remember, h prime was f of t, and then that was evaluated at x and at -6. So now we're taking a derivative. It's f prime of t evaluated at both x and at -6. H double prime of x. Then on this one would be f double prime of x. And remember, this is a constant. So a derivative of a constant is just 0 right in here. I couldn't do that earlier because I was undoing the integral. I couldn't just remove f of t, f of -6. I couldn't do that. I had to actually do the integration and kind of cancel that out with the integral. So not until the second derivative does that really cancel out. But when I'm doing h prime of 6, if I kind of use this little key over here, that'd be f prime of 6 minus f prime of -6. Kind of similar to what I did before, but instead of f, I'm doing f prime. So on a graph, what is a derivative? Well, a derivative on a graph would be your slope. This would be the slope for my problem here. So, let's see. Actually, I take this back. This right here, since this would be a constant, I take this back. This would be f of x minus f of -6. This actually will zero out because this would be a constant as well. There we go. And then I end up then with just, since that was a constant, that went away. That was like a 0. Okay, so I need f prime of 6, which is essentially the slope of f at x equals 6. So I'm going to look at my graph here. Slope here would be rise over run. And it looks like down 2 and over 4. Now, I would reduce it, but you actually technically don't have to. You actually are allowed to leave it down 2 and over 4 or negative 1/2, your choice. Okay, h double prime of 6 would be then f double prime of x. So f double prime, I guess in this case of 6, f double prime, instead of looking at the slope, is looking for the concavity of f at x equals 6. So let's take a look. What is the concavity of f? Well, this region where x is 6, we actually don't have any concavity because this is actually a straight line. There is no concavity here, so we use a 0. It's not concave up, that would be positive. It's not concave down, that'd be a negative. However, it is defined. We don't have like a vertical tangent line. We don't have a discontinuity or anything like that. So it is defined. It just doesn't have any concavity. So we use the number 0 to represent if a region or an instant has no concavity. All right, on to question 5. This is also non-calculator. So we're looking at this curve, x squared plus 3y plus 2y squared equals 48. So notice this is not written explicitly. This is an implicit equation. We are told what the derivative dy dx is. So we have this formula in terms of x and y for dy dx. There is a point on the curve 2, 4 with an x-coordinate of 3. Use the tangent line at 2, 4 to approximate the y-coordinate of this point. Okay, the key phrase on there, the first thing that really jumped out to me is use the tangent line. So let's start there, even if you're feeling a little lost. Since that's the key phrase, we do know how to do that. To write an equation of a tangent line, we need a point, and they said to write it at the point 2, 4. So that's our HK. And we need a slope. The way we find a slope is a derivative. Well, they gave us a way to calculate the derivative. They gave us this differential equation. And we're going to specifically calculate it at the ordered pair 2, 4. So dy dx, at the point I'm going to use for this tangent line, we'll use a 2 for x and a 4 for y. So we'll get negative 4 over 19 as the slope of the tangent line. So the tangent line itself would have this equation: y is equal to the slope times x minus h plus k. So there's my tangent line. Now what they told me from here is they said there's some point near 2, 4 and the x coordinate is 3. So I'm going to be using in my tangent line that x is 3. That's what I'll be plugging into my tangent line, and they want me to find the y coordinate of this. I'm approximating. The tangent line is not the exact same as whatever this curve ends up looking like. Whatever this curve looks like, the tangent line at 2, 4 is close to what the height would be at 3. So we're using it, we're finding this one and saying, hey, it's close to that one. That's essentially what we're doing here. Okay, so I'm going to find y by substituting in for x a 3. And if I were taking an AP exam, I'd stop right there. I would not bother to compute that further. If you really want to, you can, but most students make computation errors on big tests. So this would be negative 14/9 times 1 plus 4. Well, 4 is 76 over 19, and so I'll end up with 72 over 19. Again, it is totally okay, and even I would say recommended, to just leave it as negative 14/9 times the quantity of 3 minus 2 plus 1. That's all numerical on the right-hand side, so you're good. All right, part B. Is the horizontal line y equals 1 tangent to the curve? And give a reason for your answer. All right, well, if something is tangent, then it should be drawn so that it has a slope that's a derivative at that instant. So what is the slope of the line y equals 1? The slope of the y equals 1 is 0. And so what this is saying is dy dx should equal 0 at the instant when y is 1. Supposedly. All right, that's what we're trying to find out. The claim is that maybe this is a tangent line. If it ends up being a tangent line, then we should be able to plug in a 1 for y and be able to verify that we get a 0 slope. Well, if I look at my differential equation for slope, which is dy dx, I don't only need to use a y, I also need to use an x. Now for the y value, I'm going to use 1. That's exactly what they told me. We'll use y equals 1. So, and that's what I'm plugging in here. However, for x, I don't know what x is, but I can find it out because I have an original equation that relates x and y. So I want to figure out what x is when y is 1. So I'll use the original equation. Let's see, what would that be, 5? And let's see, x squared, pardon me, is 43. So x is plus or minus the square root of 43 on this one. Well, either way, whether I use the plus or the minus of the square root of 43, I'm going to evaluate this slope at plus or minus the square root of 43, comma 1. So that's what I'm going to plug in here for x. Either way, am I going to get a 0 for the slope? That is not a 0. I didn't bother to compute what it is, but it's very clearly not a 0. So no, there is not a tangent at y equals 1 is not a tangent line for this curve. All right, part C. The curve intersects the and by the way, notice they're not saying function. This is probably not a function. It looks to me like maybe some type of conic. I'm thinking it looks like an ellipse to me. The curve intersects the positive x-axis, the square root of 48, comma 0. It is interesting. Sometimes they do not simplify their radicals. Is the line tangent to the curve at this point vertical? And give a reason for your answer on that one. Okay, so they gave me another ordered pair, and they're still talking about tangent lines. So tangent lines are all about derivatives. So let's see if I take a look at the tangent line at its slope, and if I evaluate it at root 48, comma 0, what do I get? Do I get something that makes me think that this would have a slope that indicates a vertical line? Well, if I evaluate this at negative 2 root 48 over 3 plus 4 times 0, I get negative 2 root 48 over 3. Is that a slope that a vertical line would have? No. A vertical line would have a slope that's undefined. The way a slope is undefined is by getting a 0 on the denominator. It's the most common way. But this is not an undefined slope, so this is not a vertical tangent line. Not at that point anyway. There might be ones at other points, but not there. All right, part D. For some time that t is greater than or equal to 0, a particle is moving along another curve, and here's the equation for this curve. So now we have a new equation. This is some other type of relationship that we're working with now. At the instant that the particle is at 4, 2, the y-coordinate of the particle's position is decreasing at a rate of 2 units per second. At that instant, what is the rate of change of the x-coordinate of the particle's position? All right, I'm going to erase this. You can find the rest of this information by reviewing the video and just going back a bit. But I want to make sure, be able to look at the screen while I'm doing the solution for D. Okay, so let's write down the information that we have and see if we can figure out what they're asking us to do. So we're looking at the instant that the particle is at the point 4, 2. The y-coordinate is decreasing at a rate. All right, well, that is telling us dy dt, remember this is with respect to time, 2 units per second. And that's another way I could tell that this is with respect to time because it's per units. Now, I'm not going to write 2 units per second. I'm going to write negative 2 units per second. And that's because it said it's decreasing. That is language that tells me that this rate is a negative. At this instant, so we're still looking at the instant 4, 2, whenever that happens, what is the rate of change of the x-coordinate? So what we're trying to find is dx, that's the rate of change of the x with respect to time, so dx dt. Well, then I need to have an equation that can have dy dt and dx dt in it. I can get that if I take the derivative of the original equation for the curve. Be careful, we're going to do this implicitly, and there is product rule when we have to multiply x times y. Anytime I take a derivative that is not going to be of the variable t, I'm doing these with respect to t, then I have to do times dx dt or times dy dt respectfully. All right, so this would be 3y squared times dy dt. This is a related rates problem, if that's helpful for you. And then I'm going to do product rule here. So the first times the derivative of the second with a dy dt plus the second times the derivative of the first times dx dt. And then don't forget to take the derivative of the other side. In this case, it is the constant 0. After you've taken your derivative, you can start substituting. We can substitute in 4 and 2 for x and y, and we can substitute in -2 for dy dt. So as I substitute this in, this would be 3 times 2 squared times dy dt plus 2 times x. Let's see, x was 4 times dy dt again. Let's see, that probably means that I messed up. Let me check and see. Oh, nope, I did do that right. That's another -2. And then plus y, which is 2 times, oh, here we go. There's my dx dt that I was looking for. This is my unknown quantity that I want to solve for. So I need to isolate that expression. So this would be 4 times 3 is 12 times -2 is -24 minus 16 plus 4 dx dt equals 0. So 4 dx dt would equal 40 when I rearrange this, and dx dt is then equal to 10. The units would be units per second. It would be the same as dy dt. They didn't actually tell us that we have to do units, but most of the time for related rates, it is good practice to do units, but you don't actually have to. In this one, they didn't tell you needed units. All right, last one, question 6. We have two functions, f and g. They're graphed for us, and we have their expressions. They're both parabolas, as you could tell by the equation and the graph. R is the region bound between f and g, going from 0 to 2. And we want to write but not evaluate an integral expression that would model this. Okay, so when we're doing area, if we could represent things with vertical slices where one curve is above the other, we do the definite integral of the two boundaries, like left and right, and then of the top curve minus the bottom curve. And then this would be dx. So that's my plan here. So we're going from 0 to 2. They actually told us that. Right here, it's also visible in the graph. The top curve is f, the bottom curve is g for this boundary, and then dx. You are certainly allowed to write in the actual expressions for f and g. Some kids even simplify them. It is not required, and nor is it recommended because it takes time and you're more likely to make an error. All right, part B. Let S be the region bounded by the graph of g and the x-axis from 2 to 5 as shown. Region S is the base of a solid. For each solid, each x-axis, at each x, the cross-section drawn perpendicular to the x-axis, that's telling us that we're doing this dx, is a rectangle with height equal to half of its base in region S. So we're going to be taking a definite integral from 0 to 2 of the area, and that would allow us to find the volume. We're going to do this dx because we're perpendicular to the x area. And they said that these are rectangles, so rectangles would be base times height. But the height on this one is half of its base. So base times height, but that height's really half of its base. So what I could think of is this is from 0 to 2 of 1/2 b squared. And that base, which is like one of the sides of the rectangle, would be top minus bottom because we're doing these with vertical slices again. So this would be 1/2, oh, not 0 to 2 anymore. Let's see, they gave us a new interval. 2 to 5, sorry about that. You're probably screaming at the video. All right, so 1/2, I'm gonna just integrate this. So times 1/3 b cubed, we'll evaluate this at 5 and 2. Oh, hello. Let's actually put in what the top curve and the bottom curve would be. Doing awesome. All right, well, the top curve is g. So this would be x squared minus 2x, and then we have to square it because it was base squared. All right, now if I want to evaluate this, I do need to expand this out first. So when I expand out x squared minus 2x times itself, you would get x to the 4th minus 2x cubed and another 2x cubed, so minus 4x cubed, and then plus 4x squared. I'm going to now integrate this. I'll leave the 1/2 separate. We would have 1/5 x cubed minus x to the power of 4, and then plus 4/3 x cubed. This is going to be evaluated at both 5 and at 2. And this is where it becomes so helpful to not have to evaluate or not have to simplify expressions. So I would have the 1/2, and then I'm going to plug in a 5 for all of this. And I'm also going to plug in a 2 and subtract that. And I would leave my answer like this if I'm taking the AP exam. Now, if for some reason it was multiple choice and something and I did need to simplify it, then I would. But I wouldn't bother. Oops, that's a power 5. Made 3 errors on the same problem. I'm so sorry. But I would just leave it like this. I would not bother to simplify it. That was a correction right there. If I absolutely felt like I had to simplify it, I'm going to show you real quickly how you could do that. I just wouldn't bother personally. All right, so 5 to the 5th divided by another 5 is really 5 to the 4th, which is 5 squared times itself. 25 times 25, 625. It's a little painful. 5 to the 4th is another 625. Those will undo each other. 5 to the 3rd is 125 times 4 is 500 over 3. And then 2 to the 5th is 32 minus 16 plus 4/3 times 8 would be plus 32/3. These cancel out. So that's kind of nice. Kind of looking ahead, I'm seeing I'm going to need a common denominator for all these interior numbers of 15. So if I make these have a denominator of 15, I'm going to multiply by 5 and get 5 over 5, so 2,500 over 15, minus, I'll multiply by 3 and get 96 over 15. I'm also going to distribute this negative as I go, so now this is plus. I'll multiply by 15 and get 240 over 15, and then this one I'm going to multiply by 5 and get minus 160 over 15. Those all have common denominators, so I can go ahead and add all of those together. And I'm going to get 828. That's not true. It is bigger than that. I think I already reduced here. Sorry, I didn't want to waste your time on computation, but then we could reduce. Again, I would never do this. What would that end up being? And also can divide by 3. So I'm going to divide by 3 and divide by 2. So in other words, I'm going to divide by 6. Get 414 over 5. But there's zero need for us to do that in the context of what we're looking at. So don't spend your time on that. It takes way too much time. The odds of making a mistake are very high. Okay, so on to the last part, right? But do not evaluate an integral expression that gives the volume of the solid generated when region S, so we're back on this one, is rotated about the horizontal line y equals 20. So y equals 20 is all the way up here. And that's what we're rotating about. Okay, so if I'm wanting to do a rotation, my form here would be like a circle. I'm going to do an integral essentially of a circle. I have to decide, so this would be like pi r squared. And we want these to be the same region as described before. So these are still going to be drawn this way. All of our slices are going to be drawn vertically. So this is going to be dx. Also, too, since I'm rotating around a horizontal, this will be in terms of x. So the question is there empty space between region S and the line that I'm rotating around? And there is. So what that means is that this is actually washer method, because I actually have two different sets of circles that I'll be forming. I'm going to have two different sets of circles when I connect the line of revolution down to the boundary that's at the edge of this, the bottom boundary, which is the line y equals 0. And then another one where I'm connecting it to the top boundary, which is g of x. Now remember, we're just writing this. We don't have to evaluate it. My limits would be 2 to 5 again. Don't forget the pi. The longer radius is the boundary that connects the farther boundary to the line of revolution. And so that would be 20. Within this, we're still doing top minus bottom for each of these. So that'd be 20 all the way down to the y-axis, which is 0. You don't have to write the 0, the minus 0. You can just write 20 squared or 400 if you'd rather. Minus the top part of my next radius is also 20 down to the line that's connecting it with, which is g of x, and that's also quantity squared dx. And that is the end of this video.